All right. Everyone, welcome. Thank you for being here. It was, it's been. Today we have a very great presentation with one of my favorite people. There, if you don't know Charles Nutter, you know him after today, and you understand why he's one of my favorite people. But it takes something very complex and make it very easy to understand, and then it's like magic. But I wanted just to go over a little bit. We had a great year. We're winding down our essential meetings for the year. It's been fun. We actually have almost 1,200 people sign up, which is great. We want to see more of that. So, they're great. But so one thing is if you're new to this meetup, let people know. We want the Java users group to grow. And one of the easiest way for us to grow is if you bring people in, and that allows us to get great speakers, allows us to find great partners. So please do that. We actually have 28 meetups. We've been busy. One of the things that is pride and joy, we are actually the first user group to adopt the JSR. Bob has been sending emails about it, and I'll let him talk in a little bit about what it means for us. We have the mentors program. We're still available. If you have questions about Java, or you have a problem, or you're saying, I don't know this technology or this technology, should I use NoSQL or just regular SQL? Then reach out to us. We'll help out. Within all the leadership we cover a lot of from embedded to high frequency trading type deals to frameworks and web, and Cedric just does everything, so that's fine too. We presented with the women's dev group, so that's another thing that we're trying to outreach to more groups. We actually have something coming up with a couple other user groups, and one of the things that we are proud of this year is we are actually trying to get you guys to know the different companies that are here. Sometimes we don't know who is in Chicago. Groupon is in Chicago, Orbitz is in Chicago, CME is in Chicago, and one of the things that we're proud of is that we're trying to let you know, hey, these are the companies that take Chicago as their home, and we want you to reach out to them and know them. For this year, we actually started with a little bit of a makers track, and that is for those that are really geeks and tinkerers, and that's fun because you just get to play with toys, and we're going to keep doing that as we go along for next year. For next year, we actually have big surprises, but I'm not going to spoil that. You have to come to the first meeting of the next year to figure out what we're doing. For today, we're very, very grateful to both GOTO and Groupon. The GOTO conference, essentially is Trifork, and they have allowed us to have Charles Nutter here. So I'm going to let you, Alex, speak.
Go back to the slide.
Which one? Oh, yes, it is possible.
All right, well, anyways, I'm Alex. I'm with Trifork. Myself and Nile are two of the organizers for GOTO Chicago 2015, and we are excited to have our third annual year here in Chicago. This year we'll be doing it on May 11th through the 14th at the Weston River North, and it's a brand new venue for us, so we're really excited, in the heart of downtown Chicago. This year we also have a great selection of Java speakers, Chad Fowler, Jill Teen, Cameron Purdy, Josh Long, and Tom Stewart. And we also have a great selection of keynote speakers, Anita Sengupta, who is from NASA. We have Chad Fowler, we have Kyle Kingsbury, we have Martin Thompson, and Todd Montgomery. And we wanted to thank Groupon and Aaron Vedra in particular for allowing us to host here tonight, and CJUG for partnering with us and helping us host this great event. And last but not least, Charles Nutter for coming all the way from Minneapolis here. So thank you guys.
All the way from Minneapolis.
Such a long flight. Oh, and yeah, we also are offering a special promo code for everyone here until the end of December, and it's $100 off our early bird pricing, which is it's $950, but it will be $850 for registrations for GOTO Chicago 2015 for you guys. So that will be, the promo code is Nutter. Yeah.
There's an interview with Charles for this?
Yeah, and yes, great, that's really fast. It's on Ugtastic, and Mike Hall and Charles did an interview before this talk, and we're really excited to be able to use Mike for those interviews, so thanks, Mike.
All right. No, and I mean, I attended the conference last year, and actually the roster that they have, it's if you never heard these names, don't worry about it. They are like A+. So that's, yeah. If you can, go, please go, because it is a good conference. I've been there. Charles Hunt was there, and John was there. John Danovich, which is the IBM guy. So yeah, give it a shot. I'm gonna let it a little bit to Bob. He is on the back. Just an update on .JSR and what we're doing and why we're special.
Yep. So I'll be brief. What we've done this year is we've adopted JSR 366, and for those that don't follow the numbers, that is the umbrella JSR for Java EE 8. So everything that ends up going into Java EE compliant application servers, whether that's the JSP spec, the servlet spec, all of those things that are part of those application servers are part of that specification. We picked it because it's a broad one, and we just want to kind of figure out what people in Chicago are interested in, and this gives us an opportunity to kind of dabble in a bunch of different things. So I know people are very opinionated about Java EE app servers. Maybe there's too much stuff in them. Maybe there's features that are not in them. This is our chance to have a voice in that, and that voice goes directly to Oracle. So what we're going to be doing is we're going to be organizing a bunch of maker tracks and talks throughout the year on certain things that are part of the Java EE specification. And we're going to be looking for you guys to provide feedback that we can put into packages and deliver to Oracle to try to move this thing along, to get the change that we want to see. There's no reason we shouldn't be doing this and have a voice in Chicago, and we're going to be putting together events that are going to highlight that.
If there's something you heard about EE7 and you want to fix it, this is how we can do it.
We've got a Google group set up. We've got an event on the 15th. We've only got 6 spots left. We're going to be covering a JSF with Josh Junow, who is on the expert committee. So you love JSF, you hate JSF, come anyways. It's a good chance to offer feedback and see change in those products and those specifications. So that's all I got. Thanks.
Last thing is, if you being on the Java users group, you know that there's a party coming up. It's next Tuesday. It's essentially just like last year. It's just get together, have fun, be a geek, and talk shop. So we are doing this with the .NET users group, and I say don't start any brawls. We know who will win. We always win. But the idea is just to come up, be merry, and have a good time. So please come in. It's free. And there's free beer and free drink, free food too. So come and have a good time. So last but not least, there's a couple of things. Yeah, the first one is if you want to be part of helping us run the organization and be part of the advisory board. Every other meeting, we always have a sign-up sheet next to the pizzas. Just write your name down and your email, and then we keep track of this for people that want to actually participate and help us out, in steering the direction. Now, if you want to volunteer, just come talk to me. You don't have to sign anything, just come talk to me. But if you want to be part of the advisory, formally and stuff, then yeah, let's do that. Last but not least, we're going to introduce Charles Nutter. And I have a funny story about him. Actually, this was on the Trifork, the last year's GOTO conference. I was having dinner with Gil Tenner and John Danovich, which are, if you don't know their names, essentially Gil is the one that does a pulseless garbage collector. He creates his own Java version with a pulseless garbage collector. John Danovich essentially leads the IBM JVM. I mean, these are guys that essentially solve NP hard problems at breakfast, for breakfast. And seriously, we're talking about how great the Java ecosystem is, how great the JVM is, and then suddenly we're talking about, yeah, Scala runs great on our stuff, what do we think about Scala, how is it going to evolve? And then I posed the question, what do you guys think about JRuby and Charles Nutter? And then everybody, without batting an eye, both look at me and he's crazy. And there's a reason for that. I mean, Charles Nutter is the real reason why a lot of the JVM languages can proliferate. He's the one who has been pushing the buttons of everyone saying, this is wrong, we need to fix this, we need to find a way to make this better. And they were always so amazed at how he can not just keep up with the Ruby language itself, but actually make it better. No offense, Ray. He's already ignoring me. He's the leader of the Ruby users. But the real reason is yeah, I mean, Charles Nutter, he's a tour de force, and we're so excited. I've been looking for bringing him here for the longest time, and that's when Triforce said, you know, we can help you guys out, and I think it'll be a great meeter of the minds just to have him here. So with that, I leave the stage for you.
All right, great. All right, and it worked right the first time. That's great. Hi, everybody. It's good to see you all. I'm glad we got a good full house tonight. I hope everybody's enjoying this wonderful local microbrew. You guys have lots of good beer down here, which is why I came, really. But doing a talk with a beer in hand is the best way to do a talk. So I'm going to do a talk a little bit about a few different projects, some of which I have a direct hand in, some of which I'm just supporting, that are kind of pushing the edges of the JVM, solving problems that were at least hard. We knew they were hard to solve, but potentially impossible to solve in some cases. We're actually making these things happen on the JVM. So we'll have some fun with this, and hopefully you'll have some projects you'll be willing to look into and maybe contribute to in the future. So a little background, just to set the stage here. We're kind of doing this as a play in 3 acts or so, or 4 acts, where I'm going to talk about what the state of the JVM is, where we've been, what sort of things we've had to deal with working on JRuby, and then some of those projects that are making the future of the JVM as a language VM, as a high-performance VM, a little bit more interesting to us. So, Java, most folks know these numbers, released 1995. How many folks have been developing since Java 1? There's quite a few, I did applets. I did applets as a university student working in the web team in 1996, I think it was. And it was horrendous back then, but it improved a lot over the times. 1998 we had 1.2, which we obviously had some collection libraries in 1.1, but Swing came along. Tons of other libraries came along. Thank goodness we got things like Corba in there, really important libraries to have in Java. So lots of stuff was added at that point, and unfortunately nothing's been removed yet until maybe Java 9 will be peeling some stuff out. In 2000, though, was when Java really started to become a real force within the development world. That was when the hotspot JIT compiler landed and was the standard runtime for Java. You could turn it on in later versions of 1.2, but 1.3 actually brought near native performance for Java applications. And then things continued on that way. The JIT compiler continued to improve over time. The Java language incorporated additional features, generics, better libraries. Around 1.2 was when we had the first EE release. 1999 was the first Java EE. So things have continued to move. They moved very well until about Java 1.6, 2006. Things really stalled at that point. The JVM wasn't moving forward very quickly. The language was certainly stalled, completely stalled at that point. So what happened here? Well, the problem is that Apache really wanted to do their own open source Java. They wanted to work on Harmony. They had their own JVM. They had their own class libraries. And they wanted to be able to test it and then certify that it was Java compliant. But they're Apache. They're very open source centric. They wanted an open source test kit that they could use to test Java. Now the problem was that Sun had basically been pulling in all of these tests from hundreds, maybe thousands of different customers over the years. Vetting all of that code to be released as open source was way more of an effort than open sourcing Java itself. You can imagine all of those different companies that would have to agree that their test case that was specific to their application and their secret proprietary concepts, very difficult for them to release. And so Sun just said, no, we can't do that. We just can't open source this stuff. And so Apache refused to go forward voting for Java 7, and they were a primary member of the JCP at that point. And Sun could not release the TCK. It was a deadlock. And so we sat there for 5 years, basically, until we got anything beyond Java 1.6. And really it was about 4 years, so double the normal release time before we even got Java 7 moving again. And you know, as worried as people were about the Oracle takeover, this is one thing that they got moving again. They came in and they said that we can't have Java 6 be the only Java that's out there. We can't be completely beholden to retaliatory votes of no for certain companies that don't like our policies, we need to push forward with Java if we're going to keep it alive, just to save the platform. The platform was going to die if we didn't do this. So they pushed through Java 7, and okay, everyone's like, yes, we knew Oracle was going to be bad for the platform. We knew they were evil. They're even kicking community members out and not even listening to them. But over the intervening years, it's actually looked pretty good. Oracle has contributed far more resources internally, monetary resources, manpower resources over the years. They've continued to do releases. They're back to a 2-year cycle. They're continuing to do security releases on a much more aggressive cycle than Sun ever did, fixing stuff that Sun just brushed under the carpet over years. So I'm still optimistic about Oracle and their management of OpenJDK at this point. So if we look just some concrete numbers, this is OpenJDK commits. It'll be a little hard to see on the screen, but you can kind of get it. This is OpenJDK commits from the time that it was open sourced, and so trackable in the open source community. And you can see in 2008, 2009, 2010-ish, it's pretty flat. There's not a whole lot going on. That was when we were essentially stuck at Java 1.6. Had no idea where 7 was going to go. A lot of work in late 2010, in early 2011, leading up to the Java 7 release. But what I find really interesting, after the lull that happens immediately after a release, as any of us knows that we take a break after a big release, it didn't quite go back down to the same level. The next versions, as we got up to Java 8, and we're doing hard development on Java 8, trying to get that release out higher than the Java 7 numbers. And when it dropped off to a higher level again. And this has continued over time. More and more work being done on OpenJDK, not just by Oracle, but by external contributors too. We look at the community that we have for OpenJDK. There's literally dozens of companies, a lot of companies that you wouldn't even expect to be contributing to the OpenJDK, like Twitter, are part of the OpenJDK community. Hundreds of users and individuals that are doing contributions and making commits to OpenJDK repositories. Pretty much all the JVMs that you're going to run, other than the non-JVM on Android, is OpenJDK based, and it's really it's a really good open source love fest that actually is working as an open source project, even under Oracle, a company that everybody was afraid was not going to be a very good open source company. I always figured, because we were at Sun right up until Oracle, I knew all of the guys at Sun that worked on Java, and they had open source so in their blood that there was no way this match was going to be made without some of that infecting the rest of Oracle. And I think they've really done a good job of letting the Java organization continue to manage it in an open source way and an open process and all that. So it's looking good. Again, the same sort of numbers as far as contributors and commits, continuing to go up over time. And this is not Oracle adding twice as many developers to OpenJDK. Oh, they've added a lot, but they haven't added twice as many. Most of this is coming from outside. And it's people who used to compete with OpenJDK, used to compete with Sun's Java. It's platforms that Oracle doesn't support directly. All sorts of folks that are actually making this thing work. And anyone here, as you're doing with the JSR process, you can contribute. You can help this stuff, and you can get patches in. Even the smallest one will make a big difference. So then moving on from there, we joined Sun to work on JRuby officially in 2006. Hard to believe it's actually been 8 years of working full-time on JRuby at various companies. But you know, for those who aren't familiar with it, JRuby is obviously Ruby on top of the JVM. We try not to say Java when we're at Ruby conferences. We just say JVM, and they're like, oh, wow, it's magic. But it's Ruby plus the Java virtual machine, taking advantage of everything we have on that platform. And basically because we're all Java guys. We've done Java for years. We know what the JVM can do. We know it is the best managed runtime out there. Sorry to any .NET folks that are here. JVM is by far the best managed runtime as far as performance, scaling, threading, everything. It does so much better than most runtimes. We like the JVM. We don't have to do platform-specific compilation. JRuby on Windows works exactly the same as it works with JRuby on Linux or BSD. Very difficult for the native implementation of Ruby to do that and keep it consistent. No native library dependencies. One of the reasons people can't run Ruby on Windows is because the Ruby world has all these C libraries that have to compile and install. So how many Windows users do you know that have C compilers installed if they're going to do Ruby development? Not generally. Or Java development. you have to pay for that kind of stuff, or you have to go and struggle with stitching together Ming W32 or whatever. It's a big problem for folks trying to run Ruby on Windows. They don't have to deal with that with JRuby. Of course, we get the advantage of Hotspot itself. JRuby is the fastest, like, standard production-ready Ruby implementation. There's experimental ones that can push it a little farther, but if you're going to run Ruby in a real application, you run it on JRuby because it's just faster and it scales and threads right like you'd expect it to. And really the JVM kind of ends up being sort of a magical black box that just makes our code work, makes Ruby run fast. We love being able to just throw stuff at it, know it's going to work, know it's going to run consistently across platforms. So there's lots of things to like about the JVM, which makes, these are obvious reasons why this would be a better approach to building a language runtime than starting from scratch and building your own garbage collector and your own JIT, right? But there are issues. There have been challenges along the way to get Ruby to run well on top of the JVM. It's very much tailored towards Java. It's mostly had to host Java, and that's where Sun's focus was. Even Oracle still largely focuses on Java, so other languages have challenges. When you do need to call out to native code, it's nearly impossible on a standard JVM. There are libraries that can help, but they're not standard. It's something somebody else has to ship, potentially build additional code for. And this black box that we love so much, we have to guess. We have to throw code at it. We have to tweak flags from outside, inlining things and hotspot and GC tuning and whatnot. But other than that, we can't really see what's happening behind the scenes, and we certainly can't influence what's happening behind the scenes. We can't tell the JVM how to optimize Ruby the way we want Ruby optimized. And so all these areas are things that we've been exploring over the years, starting to come up with solutions for. Because we want to do Ruby on the JVM, we want this to work. Let's look at a few of the projects that are actually making this happen, that in the future may make the JVM even better, maybe make it the best runtime for any language, rather than just the best runtime for Java. The first one I talk about is Invoke Dynamic. How many folks have played with Invoke Dynamic at all? All right, that's about what I thought, like 2 or 3 people. It's a very obscure feature that came in Java 7, but had no exposure to Java the language in general. So most folks don't know what it is, but it's the underpinnings of everything that you're going to see in the JVM for the next 10 years. And so it's really important to understand what it actually can do and how you and how the Java language designers are going to be using it. All right, so again, a little bit of history. The JVM authors did mention non-Java languages in the original JVM specification. They talked about having targeted extensions to the JVM at some point that maybe were just for other languages than Java. They knew that this was going to be a good generalized platform to build stuff on, but it was not really focusing on other languages than Java at the beginning. And over the years, hundreds of authors have targeted the JVM. There's an implementation of pretty much every language out there that runs on the JVM of various qualities. Sometimes there's 2 or 3 of them. At one point, I think there were 3 or 4 different Ruby implementations that ran on the JVM. And JRuby was obviously the most complete, so we've kind of taken that over. The problem, though, is that the JVM was a mismatch for a lot of these languages. Dynamic dispatch is one of the obvious cases. The JVM mostly wants statically typed dispatch. It's got to be compilable to that call. So we had to do tricks to get around that and do our own optimizations. There's also features that the JVM could not provide, like coroutines, generators, threadlets, whatever you call them in your language. Still not supported on the JVM. We've had to find other solutions to make those work. So if we look at what the JVM itself is as far as a specification, it really is just a set of operations, a set of opcodes that have particular behavior, and then a little bit of logic about how it's going to run at runtime. So we've got invocation, we've got field access, arrays, kind of the endpoints. This is where data flows through the system, flows into a call or goes into a field or an array somewhere. And then there's a bunch of other miscellany sort of things, stack control, flow control, math stuff, things that don't have direct side effects outside the VM but are necessary for the flow of the program to work properly. And so traditionally, if you wanted to build a language on top of the JVM, this is what you had to work with. And if you needed an operation that was not supported here, you had to aggregate them together, you had to build libraries around it, you had to do neat tricks at the bytecode level to try and get things to work. But for the most part, you had to kind of stay inside this little bubble of what features were available on the JVM to implement a language or a library. So this is the quote I mentioned earlier. In the future, we'll consider bounded extensions to the Java virtual machine to provide better support for other languages, not for Java. And for the first time in Java 7, that actually happened with Invoke Dynamic. It was a bytecode added to the VM that Java did not use in any way. It was only for other languages, and then potentially because of the ability, the power of the feature, for features in Java, the language in the future. But added to the JVM without any Java support of any kind. So this is JSR 292, for those of you following along. Invoke Dynamic JSR. It's essentially a user-definable bytecode. It's a bytecode that you can put it into a piece of code, and then rather than executing some arbitrary sequence of operations, the JVM calls back to you at runtime and says, what am I supposed to do here? And then inserts that into the code at that point. Optimizes it as if it was written as static code. So you can do your dynamic lookup of methods. You can lazily allocate constants and cache them in place, and they optimize as if they were there at compile time. Lots of stuff that you can do. Basically, all of the VM behavior you want, you can plug into this user-defined bytecode. It also comes along with an API you might have seen, Java Lang Invoke, the method handle API, intended to be essentially fast function pointers, faster than reflection, with a bunch of adaptations you can do. If you want a function pointer that also rescues or catches exceptions and has different behavior, have it in one object without having to write any code for it. It's a programmatic way to build up essentially a function object. Caching and validation, all sorts of VM level things, like caching methods, invalidating when classes change, so on. So let's look at what this actually looks like in practice. So here's the invoke side, and this is what we've had traditionally on Java 6 and lower VMs. We have our static invocations, or system current time millis and so on. We have virtual dispatch, which is dispatch against a concrete type. We have interface dispatch, where something has been casted to list or collection or comparable, and we make a call against that. Additional plumbing within the JVM to find the right interface method and make the call. And then we have what's called special invocation, constructors and super stuff that goes through visibility, only works within certain contexts, and so on. And so if you look at these at the bytecode level, we have invoke static, invoke virtual, invoke interface, and invoke special. And this is pretty much the only ways that you can invoke or cause external code, external subroutine, to be executed on the JVM prior to Java 7. Now, if we actually boil these down to their actual VM level operations, the things they do at the VM level, what you'll notice here is that with a few differences, this is largely the same set of operations for every single one of them. You pretty much just take an object in hand or a class, you find a method on it, you cache it somewhere so you don't have to do that lookup again, and then you invoke it. And then ideally you just keep going back to some cache and calling the method directly. If you have more complicated lookup logic, you can't get that out of this. You've got to wire it yourself. If you have different semantics for how you invalidate that the method is still the right one, as in Ruby, where you can rewrite classes, modify methods at runtime, nothing that we can do as part of these. And that's where Invoke Dynamic came in. Invoke Dynamic basically says, we've got all of these little primitive VM operations that we can use for method lookup, method dispatch, caching, and so on. Let's let you decide how to assemble those together, and we'll just give you an entry point in the code. You stick an Invoke Dynamic bytecode in the code, you tell it how to do all the dispatch, how to do all the caching, and the JVM pretends it's one of these other built-in operations, optimizes as if it was always there. Very powerful. Much more than just dynamic invocation, much more than dynamic typing. You can do almost anything with this. And it's really interesting to see the evolution of the Java language now starting to use some of these features. So to go a little bit more graphically on this, on the left here we have our code, essentially our router for the system, and the JVM is on the other side, figuring out which methods we want to call as these different endpoints for our switchboard. So we've got some Invoke Dynamic bytecode that comes in. We want to make a call, basically. We don't know where it is. It's some arbitrary object. We just want to call this method. Maybe it has these types. Make the invocation and make it work. So the Invoke Dynamic bytecode, the first thing the JVM does is call back to us to a normal piece of Java code called the bootstrap method. The bootstrap method says, all right, I'm going to go get a function pointer. I'm going to reorder the arguments a little bit. I'm going to do some type checking here, and then I'll put some caching around it to make sure it's still the right method every time. Once we've got the bootstrap method, we've got it all set, we know exactly how we want this invocation to work, what sort of method we're going to be calling. That goes into the method handles. That's where we actually stitch this stuff together. So we've got our handles that we give back to the JVM. The method handles go back to some target method. They actually do the invocation of whatever the target is with some adaptations, with some caching. And then from then on, the JVM is basically able to make that call directly. It's gone around this whole process where we're now the JVM. We're making the decisions about how this call is going to proceed. And all the rest of this can basically just fade away. Maybe it'll invalidate. Maybe we go back through this cycle if we have additional types. Maybe a class is reopened and a method changes. But generally, this is going to go straight through. And you can see this at the lowest levels, at the assembly level. The call from an invoke dynamic to all of that extra logic that I wrote optimizes as if it was just plain Java bytecode. It's amazing the way it works. So what can we do with this? It's very abstract. I want to try and get into more concrete examples. So obviously the languages that are built on top of invoke dynamic, like JRuby, are getting great benefits from this. Rather than building all of our own plumbing to optimize dynamic calls, to optimize in Ruby constant lookup isn't really constant, it's sort of a lazy constant. This is the sort of stuff that we can get out of invoke dynamic. We can do invoke dynamic to make calls fast, to make this other stuff work well. JRuby is at the forefront of this. Groovy's now starting to look at it, Jython, some of the small type implementations, and of course Nashorn and Dyn.js. Nashorn being Oracle's new JavaScript implementation. Dyn.js is Red Hat's, because we have to balance everything all the time. I work at Red Hat, by the way, just as a preliminary there. But yes, lots of languages using this, and lots of languages getting benefit. Let's see what it actually does in JRuby. So in JRuby, I mentioned method dispatch. So our invoke dynamic, when we have a call to a dynamic Ruby method, we go to our hierarchy of Ruby classes, which are essentially just hashes. We look up the method, get it in hand, we cache it in place, we wrap some invalidation around it, so that if that class hierarchy changes at all, we dump it. And then the next time you do that call, it'll go and look up again, make sure it's got the right method. And it works very well for method dispatch. I mentioned constant lookup is also kind of a lazy constant. So we retrieve the constant, we cache it, and then if we ever see this constant redefined, we invalidate it, put it back in place. But the JVM can see through that, optimize it for the fast path. Normally it's not going to be invalidated. It'll optimize as if it was just a regular literal constant in Java code. Performance-wise, so this is JRuby performance versus Ruby 1.9.3. These are the numbers for JRuby on Java 6, not using any invoke dynamic features, using our own plumbing. And of course, we're faster than CRuby is. They don't have a JIT, they don't have the GC that we do, but not as good as we'd like to see. And these are actually older numbers. I need to rerun these on more recent JRubies. But with invoke dynamic, we at least 2 times faster than running with standard JRuby. Sometimes 2 to 5 times faster than regular JRuby for the cases that really optimize well. So it is helping us a lot. Perhaps more concrete here, this is actually an implementation of red-black tree. So this is the pure Ruby version running in CRuby. Ruby 2.0, we're on 2.1 now, but the performance is about the same. So 2.5 seconds to run this benchmark, which does adds, deletes, traversals, searches, and whatnot. There is a C extension to improve the speed of that. And you can see here why the Ruby community has such a problem with C extensions. The Ruby implementation is not fast enough for you to write C-fast code in Ruby. So there's this plague of C extensions we've had to deal with, like the red-black tree, like other libraries. It does give a good performance improvement here, brings it down to about half a second for this particular benchmark. But this is the interesting one. JRuby with the pure Ruby red-black tree running on invoke dynamic, almost twice as fast as CRuby with the C implementation of red-black tree. And now some of this, of course, the benchmark's going to optimize better just because it's running on the JVM. There's better GC that we have that improves performance a little bit. But this is still incredibly impressive. This means that if we were running on JRuby in the first place, using invoke dynamic, we wouldn't have to go to C for this to get that level of performance. Maybe we'd want the 0.1 second that we get out of the native JRuby Java extension. Maybe we don't. Maybe this is what we looked for. And so that's where Invoke Dynamics making it possible to build better languages, faster languages on top of the JVM. Now this is why I alluded to this a little bit, but in Java 7, nothing used Invoke Dynamic. None of these features were actually touched as far as the Java language. But definitely in Java 8 and 9, this is going to be used heavily. So the first one, the most visible one, is the lambda expressions in Java 8, the closures that we've always wanted in Java. Rather than just doing this like inner classes, where every closure would spit out a nasty little .class file to go along with it, with $signs and numbers and stuff all over it, they actually use Invoke Dynamic to lazily generate that little function class, cache it in place so that they don't reconstruct that inner class every time. A serious problem with anonymous inner classes, for example. You've got to spin that object every single time. And all of the shared state, all the local variables that it references, are passed in on the call stack. So the JVM can optimize straight through with no allocation, no extra class files in the jar or on the disk. It's all just Invoke Dynamic, figures out what this function object is, sticks it in place, and then passes it along to the rest of the system. Huge improvement over what we had as far as inner classes go. Yes, in front.
Sorry, I have a question. So I built a framework similar to Active Record in Java, and in order for it to have really elegant API, I had to do some code manipulation, bytecode manipulation, post-compile. In other words, there's a step of bytecode instrumentation, where it actually grabs some code from the superclass and sticks it into a subclass.
Sure.
So it's been working like a charm for the past 5 years until we hit the lambdas. So the bytecode instrumentation has two capabilities. You can do static bytecode instrumentation. That is, after compile, you generate a class,
Right.
and then it works with lambdas perfectly. But it also has dynamic, where we actually have our own dynamic class loader, which looks like, and that falls apart completely if the instrumented code is used inside lambdas.
Sure.
So I was wondering if there is a way to do static lambda generation instead of static.
To statically generate the lambdas, I'm not sure. The recommendation I'd make to you would be that maybe Invoke Dynamic would actually be a way to solve your dynamic class problem. You can basically have an Invoke Dynamic that then does that generation. The JVM will inline it as if it was just regular code, and then it is part of the original body of code itself. I don't know if there's a way to eagerly generate all the Lambda stuff. It's one of the things they wanted to avoid. Everyone hated the fact that there were all these little class files that were spit out for anonymous classes and whatnot.
Yeah, they're good packaged.
But it's probably something that you could look at as far as the generation you're doing. And I've actually wanted to work on some tools that go back and rewrite static Java code to do dynamic things using Invoke Dynamic. It'd be very easy to just plug the bytecode in and have it do anything we want. So something to look at.
Thank you so much.
Sure. So this is an example of fairly normal, fairly boring use of a lambda in Java 8. We've got collections.sort. Input is a list of string, and we're just sorting them based on their length. So the closure here, the lambda basically takes those two strings, gets their lengths, and does an integer compare so that we got the right ordering. The code on the top, 0 through 9 there, that's the code you see above. And that's all of the code you see. It loads the list, the input list of strings. The invoke dynamic goes out and generates that lambda, that closure object, and then invoke static is the comparator call. This would be much more code if you were going to use inner classes. It would have to construct that class. It would have to pass in all of the local state that it's going to need. Not quite as clean as this. The code on the bottom is what's actually in the body of the lambda, actually in the body of the closure. So it's going to load the first argument, the first string, get the length, load the second argument, get the length, do the comparison, and then return the actual integer value. And that's all magically done behind the scenes. The little pseudo method that's created here gets stuck in the same class as a little hidden method. Invoke dynamic goes out and generates a little comparator wrapper around it at runtime, and that's what's actually passed to the sort method. So you don't have any extra classes on the disk. It passes all the state through as arguments. no allocation, much better as far as performance, allocation, and other stuff. One that's coming up in 9 that I'm really excited about, another interesting use of invoke dynamic I never thought of, doing primitive specialization of generic collections. Something that people have wanted for a long time. Of course, with generics in Java, all of those types we put in our code and spend this time cultivating are all erased. They mean nothing at runtime, which means that they all have to be object. So there's no way you can do an array list of int or a hash map of ints to ints without it being essentially boxed integer objects, and you've got all that memory and allocation overhead to go with it. Well, in Java 9, they actually have prototypes now of full-on primitive specialization of collections. And the way it does is again through invoke dynamic. If you want to instantiate a collection that is normally generified to object, but you want to instantiate it with one of the primitive types, then that becomes an invoke dynamic. The invoke dynamic goes out and says, okay, I don't know what an array list of int is yet. I'll generate that class at runtime. So I have an array list of int that's actually an int array that actually has int arguments. And that's what you get back. It fulfills the contract of all the code you want it to run with, so you can do int operations without any allocation. But it's all generated behind the scenes when invoke dynamic hits it. Really cool stuff. So where else are we going with this? We're working to kind of pre-optimize more of our code above invoke dynamic. Rather than leaning on it for everything, use it for the important parts of JRuby. Invoke dynamic does have a bit of a dynamic cost, as you might expect. It's not statically optimized, so it has to run code before it can run code. There's a bootstrap time, there's startup time issues that you have to deal with. So we want to use it where it's really useful and where it's really important. The JVM folks are working on the startup issues and complexity issues behind the scenes, try to figure out how to optimize this, share more of the method handles, share more of the functions behind the scenes. But there's also this opening question about what about languages not on the JVM? There are crypto libraries, there are message queues and databases out there that we don't necessarily want to wait for someone to write a full Java implementation of that library or of the clients. We want to be able to use the same Redis client or the same ZeroMQ client that the rest of the folks in the organization writing Ruby or Python are using. So that's the second area I want to talk about. And this is one I've been working on directly and trying to push forward. Native interop is a more first-class concept at the JVM level. So if we look at the world we live in here, the bubble, again, of the JVM that we live in, we've got our JVM up here. We've got all this cool native stuff that we'd like to be able to use, and some of it's not even that cool. It's like symlinks. We didn't have symlinks for years. We still have sort of limited file system metadata. Every time a new operating system version comes out, there's operating system level features that we just can't do. We just can't do them. We have to write some J&I code or something to do it. We want a better bridge between these two worlds so that as the platforms we run on evolve and the libraries that people use and the databases people use evolve, we can use them immediately in the JVM world. So there's something missing here in the middle. This is a quote from John Rose. He is the JVM architect now at Oracle, pushing it forward and deciding on the new features. And he's really excited about interop and making this seamless on the JVM. And I like this quote. I think it's absolutely true. And this is something that we have we put blinders on. We've put our head in the sand when these libraries came up and these cool things in the native world we wanted to be able to use, or just other language runtimes that we wanted to be able to call out to. Couldn't do it very easily. We just ignored it for so many years. We'll boil this down to something very simple. What if we just want to manage the process and get the process ID from within the process? So an application, a server starts up, it dumps a process ID out to a file. We've got God or Mod or something that can then look at that file and know what processes we have available, do some system level management. You can't do this on the JVM. It's not possible to get your own process ID. And actually, if you go and look on Stack Overflow or anywhere else, the recommended solutions for this are to go into like some internal JVM API, and there's a string that happens to have the PID in it. And if you parse that string and chop the pieces off, you can get the PID of the current process until they change the format of that string or whatever else. It's nonsense that we can't. This is a trivial call. It returns an int. It takes no arguments, and we can't do that. So there's an obvious gap here for just basic things. Here's the function prototype for this. The PID-T is generally just an unsigned integer on pretty much every platform. This should be easy to do. We should be able to say, I want to call a simple function that gives me an int, do it, and not have any of the nonsense. So let's see how we actually do this in traditional Java. Has anybody done JNI before? I think it's the same hands for the invoke that are pretty close, about the same number of hands. It's horrible. You really don't want to do it. Ask one of these guys to do it if you have to do it. Let's look at what it looks like in JNI. So in JNI, we've got our user code at the top that needs to make some getPid call. We have the actual getPid endpoint function prototype on the Java side. There's some C implementation on the other side that represents the C code that makes the getPid call for us. And then the target library, which we didn't write, libc or whatever. And this is deceptively easy to begin with. You look at this and you're like, okay, getPid, stick native on it. Sweet, it's done, right? I can call getPid now. Well, it's not quite that simple. We also need to generate the header file that goes along with it. And obviously for getPid, this is about as simple as it's going to get as far as the header file. And it just gets crazier from here. Not to mention all of the JNI APIs and having to know all their nuances, all the different ways of invoking back and forth between JNI and C. Pretty heinous stuff. The implementation isn't particularly bad except for the incredibly long function prototype here that has to match exactly, the symbol has to match the package name. This is all, most of this is generated, but you have to make sure these match up as you evolve your code over time. If you move code and refactor it on the Java side, this all breaks again. It's just a nightmare. So assume that you've got all this in place and you've managed to get your JNI library to compile and it works. Well, somebody else is going to have to compile this library. And they're going to figure out all these flags. And it took me like 20 minutes to look up and figure out all the different libraries on OS 10 I needed, which headers were where, try to get this stuff to compile right. And then I have no idea like what it's going to be on OpenBSD or something if somebody's going to run the same thing elsewhere. You have to do this for every platform and build it yourself and ship binaries, or you need to have a build process that your users go through to build this library. It's silly, it makes no sense. We should be living within this managed world and just send them a jar and they're done, right? So there must be a better way, and there is a better way. The problem here is that we're writing on both sides of this line. That's the real issue. We have to write all the Java code that goes with it, but we're not done there. We actually have to do even more heavy lifting and no C. And like really no C. If you've ever, for the folks that have done JNI, you really have to know how C works and how these references and pointers are being passed around. This is not just, I'm going to write a couple lines of code like I did in the university. This is hard stuff. And so nobody does this. Nobody wants to do this. And they kind of knew that when they came up with JNI, that no one's going to want to do it. They kept it from being like JRuby with all the extensions, right? But we want to do better. So ideally, what we want is just to write our user code. We say we want to make a native call, and it makes it. It does it for us. Everything from there down should either be generated or already exist. And that's what we get out of JNR, the Java Native Runtime. So Java Native Runtime is just a Java API for calling native functions, native libraries, and allocating native memory, and so on. It has a bunch of runtime libraries that support it for pre-bound libraries, for doing specific types of libraries. Some of you may have used JNA before. You may be using JNA now. Same basic thing at the core library level, but we've made a lot of improvements over time. And you'll see this term FFI a lot, foreign function interface. This is essentially what we're talking about, being able to call out to foreign functions, functions that are not part of the rest of the JVM. They live in some library, some language that is outside the platform. And there's the JNR organization on GitHub has all the projects that I'll show you here. So in JNR, this is our entire getPid implementation. There's no C code, there's no header files to generate, there's nothing to build across platforms even. We get all of this for free. And all we have to do essentially is say we want the getPid call, which we know is going to return an unsigned integer. We represent that as a Java long, so we have the full 32-bit unsigned integer range. And then we get a library loader. We create a new instance of that loader for our getPid interface, and then say what the library is we want to load. It'll prefix lib or whatever on it. So this is libc. That's where we get getPid from. And then we can call it, and that's all there is to it. We don't have to write any JNI code. This is much better, right? This is what we want out of a native interface. So I mentioned there's a native runtime. Lots of different libraries that I'm going to cover some of these in brief here. First of all, I mentioned that we don't have to recompile. There's no build time that you have to do to support these native calls on different platforms, and that's because we have done that nasty work of pre-building this stuff. JNR, the core library is JFFI at the very bottom. That's the last library that actually lives within the JVM. And that ships with binary support for all of these platforms here. Any platforms that aren't on here that someone's using? Anybody got a really weird one that I haven't done yet? I think we have OpenVMS and AS400 builds, which is pretty impressive. That we
Dragonfly BSD?
Dragonfly BSD, I don't have a build for that. But any of the BSDs would probably be pretty easy to support. We don't have ARM64 on here, but that's pretty much because nobody has an ARM64 they can build it on right now. But like ARM support for Linux should work with Android. So we got pretty much every platform that you want to run on, and several that you really don't want to run on are covered here, and you don't have to write your own native code. Just use our library. This is in Maven. Like, you can put this as a Maven dependency. It pulls down the native jar, unpacks the library to where it needs to, and you're good to go. So, and if there's something that's missing, let me know. We can add it to it. It's really easy. So you're not going to use that low-level library. That's just like invoke some raw function pointer with some raw function memory, you know. So you're not going to deal with that. JNR FFI, though, is the user-facing API. This is kind of the basic one that you might be using in the future. This is roughly equivalent to what you get in JNA, where you say, I've got a function, here's its parameters, here's how they look in C, and here's the library it comes from. Bind it all for me, and let me call it. And of course, I mentioned structures. You can do structure layouts. Here's my structure with these many bits are this type, those many bits are that type, and it maps them into Java and back and forth. And then just raw native memory access, being able to do a malloc and a free from Java code. There are lots of cases where you actually need to be able to do that. So I won't go into the details of JNR FFI. You can kind of imagine what it would look like if you were writing basically C client code in Java. That's essentially what it does. JNR POSIX. We recognized that there were a ton of functions that everybody was going to bind. Essentially, all of POSIX, somebody's going to need one of those things at some point, symlinks or exec or getPID or whatever. So we've been slowly adding to a corpus of functions, pre-bound versions of POSIX libraries, POSIX functions, across several different platforms. Mostly the primary platforms supported BSD, Linux, Solaris, and then the ones that work on Windows are also in there. And it's largely been driven by what JRuby and Jython have needed. So a lot of people use Ruby for system-level scripting. So we've got a lot of file system APIs that are bound. Now JRuby is using a lot of native file descriptors, native I/O channels. So we've got a lot of things for opening raw sockets and opening raw channels and so on within this library. The goal is to basically have 100% of POSIX bound to this library, so you can just load it up and essentially have libc from Java. Just like that, done. And most of what you're going to need is probably already there. This is a small subset of what we have. Again, a little small on these screens, but some interesting ones. So getPID is up here, exec at the top, chmod, chown, stuff that you still can't do 100% of with blessed Java APIs. Actually modifying the environment of the process so that child processes will see that environment. Down at the bottom, POSIX spawn, that gives you actually a good version of process builder rather than the hacky, broken one that we have to deal with these days. Lots of stuff here. And again, I said this is a lot of. There's only a subset. I think fork is bound at the top and really crashes the VM impressively. That is not one that you want to use for anything. The JVM has way too many threads, way too many signals going on. Fork is like just stabbing it in the eye. It just dies very impressively. This is all you need to do. You pull the library in as a Maven artifact or as however you do your dependencies, and then run this. My POSIX handler just has a few functions. Do I have that? No. My POSIX handler basically says, when I get an error, like a -1 response at the C level, do you want me to just return that response so you can look it up, or do you want an exception, callbacks for that sort of thing? How do you want errors handled? There also is a concept of the current working directory. A lot of C functions will want to, well, at least a few C functions will want to change the directory of the whole process. Obviously not a good thing to do if you're running in the multi-tenant environment. So there's a simulated current working directory that's part of JNR POSIX. So on top of some of this, we've built other libraries. Obviously, once we have the core underpinnings of POSIX and libc, there's more cool stuff that we can do. And ENXIO is the next one, Java Extended Native Cross-Platform I/O. It's a very long and complicated name. It basically just means NIO channels that wrap a raw file descriptor. So any file descriptor you can get from any place out there, standard I/O, Unix sockets, weird socket types, you can wrap it in a standard NIO channel, select on it, do all the things you're used to doing with regular NIO, but it's those raw channels. Here's an example of the native socket channel for if you're doing a raw socket, a socket type that the JVM doesn't support, like a Unix socket, for example. You get that file descriptor probably through a socket call at the libc level, pass it in here, and then from then on it's just the channel. It's selectable, it's interruptible, it's got all the features you expect out of NIO, but it can be any native descriptor. And then of course on top of that, I mentioned Unix sockets a few times. We do have JNR Unix socket as a library that you can pull in if you have an environment where you want to keep your Postgres or MySQL local to that system. You don't want to open up TCP ports for various reasons. You can actually do Unix sockets locally and have it be totally secure and potentially a little bit faster because it's not doing all the TCP protocol overhead. Stuff like that, very easy to build on top of these libraries. So what are other things we can do with this? Well, obviously with native I/O, symlinks, we've got all of the stuff that was added in NIO2 and more. File system walking, file system event APIs, just managing unmanaged memory so you're not taking up a lot of garbage collector heap space. Selectable standard I/O and subprocess I/O. You can't do that on the JVM right now. You can't grab system.in and wait for input on it. You can spin and hope that somebody will eventually put input, but you can't do like a native system level select on a standard in, which really sucks. It even sucks more when you're trying to manage a subprocess and you're feeding it some data and waiting for some data to come back. You got to spin up a thread that essentially blocks on that API. It's gross. All this stuff you can do with ENXIO and it's much cleaner. I mentioned different different socket types that we can't have access to normally. And then new APIs, graphics APIs, crypto APIs, operating system features, stuff that we'd have to wait for the JVM gods to eventually add as a feature to the JDK. We can just go and do anytime we want. So that's pretty cool. I got to talk a little bit about performance because this is one of the big things that we enhanced above and beyond JNA. So for performance, we've done a lot of work to make JNR as fast as possible. All the code leading up to the actual native side is generated so that it's at least like one or two hops at most. On the JNI side, we actually generate the assembly code that goes from the JVM to your target function, only doing the overhead, only doing the object management, GC calls, and whatnot that are necessary for this particular invocation. And then the two sides come together actually about as fast as you can get without removing JNI from the equation altogether. We still do have to call through JNI because that's the standard interface to do native calls. And I got to show some numbers, of course. So this is JNA versus JNR. Who has used JNA before, the Java Native Access Library? Okay, there's a few folks. A lot of folks ended up turning away from it early on because the performance was so bad. And you'll notice this is a log 10 scale here. So JNR is roughly 10 times faster than JNA at calling down to a trivial C function. We can even make it a little bit better. If you don't care about the error no, the C level error that comes out of a function, you can tell JNA or JNR, don't save that, don't capture that for me. It stores it in the thread local so that you can retrieve it later. Just throw that away, and then you get like another 20-25% improvement on top of that. And then comparing this with the rest of the world out there, here's our two JNR numbers. The JNI numbers are actually the circles here. We're doing better than writing this JNI by hand. And I ran these numbers over and over again. I couldn't figure out why. Since we're actually doing JNI calls, how could we possibly be faster? The only thing I can think is that the assembly that we're generating on the JNI side actually cuts out some of the call stack, call protocol overhead that you would normally have with plain C code, and is able to make that direct call much more quickly. But so it's safe to say we're at least on par with JNI as far as doing native calls from Java code. Now, of course, the X's along the bottom, that is GCC, doing the same call to get PID. In some cases, this may completely optimize away. It seems to be doing some work here. So there's more work to be done. And this is where JVM Futures come in. So Project Panama is a project I'm involved with. This is my JEP that I proposed. JEP is a JDK enhancement proposal. That's for internal APIs or internal changes to OpenJDK that may or may not have a public API at some point. So JEP 191 is essentially adding FFI at the JVM level. And that means in the bones of the JVM. The JIT knows about this and can optimize it down to direct calls. The class libraries will know about it. We'll start to implement things like NIO on top of this FFI support. Rather than having this big blob of C++ code to deal with all the time, we can just write it in Java and use these libraries. So it's moving along. Some of the newer features that have been proposed is having a native function pointer method handle. Like from Invoke Dynamic, you'll have a method handle that essentially represents a C call. And then you can put that anywhere. You can stick it into a call site. You can pass it to someone else. But it is just a C function pointer that you call from Java. So all of the same freedom we have with Java Reflection in native calls. And then native memory layout manipulation. All these things dovetail together. We've got the need to be able to lay out structs in a specific memory orientation to call out to C functions. And at the same time, all the people that are worried about concurrency and cache locality want to be able to lay out vectors and lay out heterogeneous arrays so that they're not doing multiple hops in memory. All this stuff kind of plays together as having a better native story, integrating with the platform better. And so hopefully Panama will bring us a lot closer to having that. Now the third area, the final area I want to talk about is the most wild and experimental area that's happening on the JVM right now. It's the projects out of Oracle Labs, Graal and Truffle. So we look at traditional JVM, what we have here. We've got our JVM language that maybe it's just Java, or maybe we're running Ruby or Clojure, but we control that. We can decide how it's optimized and what the language features at that level are. That probably is going to emit JVM bytecode at some point, because that's the way we're going to get the best performance out of the JVM. We feed it bytecode, the JIT takes it, spins on it, and gives us something good. But after that, we can't really control anything. And that's our black box over here. This is all that C++ that's hidden under the covers of the VM. Stuff that we can tweak it through flags, but we can't directly say, okay, this is a Ruby dynamic call. It's okay for you to optimize this check away or that check away. We can't be explicit about it. Or this Ruby string is only going to be used for this method call. Just use the string data. Just don't actually allocate the object. Allocate it on the stack. Optimize it like you would if you were going to write it in C, for example. We can't do any of that with current JVMs. And that's been a challenge for us. We've found various tricks, but it's like writing our code to hotspot, trying to figure out how to structure our code so that it fits directly into that slot that's going to optimize well. It's too hard and it's fragile. So what if the JIT itself and the bytecode and all that stuff that happens in that C++ part was also just written in Java? And it was just an API we could call out to. And we could tweak it, and we could change some of the language semantics. We could tell it how to do better memory layout or avoid object allocations altogether in certain cases. We could make native calls directly. When we compile this, when it jits down to assembly code, we'd actually be able to do a direct call into C, rather than having all the J and I overhead on top of it. So what if we could do this? Well, that's essentially what Graal is. Graal is a 100% Java-based JIT. It runs on top of the JVM. It can emit native code for various platforms. The assembler that it uses is also written in pure Java. So 100% Java, JIT, all the way down to assembly. If anybody's ever looked at other pure Java VMs like Maxine, Maxine was the incubator for several projects, including Graal, the JIT framework that came out of it. I mentioned it emits assembly. It can also emit the intermediate representation that Hotspot itself uses. So if Hotspot is maybe better at allocating the right number of registers, deciding on memory layouts, or deciding on how to allocate objects, Graal can emit Hotspot IR, essentially Hotspot assembly, and then it continues on with the rest of the optimization pipeline. But the important thing is that you can route around JVM bytecode, which is kind of cumbersome at times if you want to optimize stuff, and you can directly control how all that code is generated. You can essentially say, I want a memory move from here to here. I want to put this object in a register and leave it there. All these things that we can't do at the JVM bytecode level, we can do with Graal IR. Looking at this more graphically, we've got our JVM language, and we've written that. We control that. We have our, we emit Graal intermediate representation rather than JVM bytecode. Rather than go down to what the JVM knows, we use this other form that's a little bit more rich and has platform specifics, platform details, memory locations and registers and so on. That calls over to the Graal optimizer. Again, this is still all just Java code, Java APIs that we're using. And then our optimizations can plug into this whole process. We can tell Graal how we want to optimize this language if we want to change it from the usual semantics. And then Graal will eventually emit that native code. But we control so much more of the process when we run on top of this library and on top of this platform that it's very promising for languages. Now the problem here, even though we control all this stuff, is that the Graal IR is pretty dense. If anyone's ever taken a compiler's course that has like a 3-address form or an SSA form, this is complicated stuff to write, and you need to be a compiler author to be able to emit this IR. You can do amazing stuff with it, but you need to be a compiler writer and a platform expert to know how you're using the registers and memory in x86. So we don't want to have to do this for all of our stuff. Right, so it's a low level, very non-trivial. You need to understand JVM internals as well, when you need to call back up to the JVM to do GCs, how it's going to be moving objects around, pointer translation as the GC juggles stuff around. It's too much for us to do. Powerful tool, but maybe a little too powerful. So the dream, if we get back to what we actually want here, is that we design our language up at the top, and then somehow we just throw it out there and it makes things work, and it's fast and it's profitable, and everyone wants to run it, and it's the next greatest thing. So the intermediate steps here, ideally this is all we should have to do. Write the language semantics into a simple interpreter, and we're done. Because everybody can do this. Everybody's written an interpreter for even a small language at some point. Just something that walks through a very trivial graph and does something based on that graph. You've written an interpreter. Now, what if that could actually optimize and have its own JIT and be as fast as writing a native runtime for it? And that's where Truffle comes in. So Truffle is the other big project that's coming out of Oracle Labs right now. It's a language framework built on top of Graal. So it uses Graal as its intermediate format, as its back end, rather than the JVM. But this is truly designed to fulfill this dream of getting a language to profit fast. You implement your interpreter. You tag that interpreter with some annotations that say, here's a fast integer path, here's a fast 64-bit long path, here's how you promote a long to my numeric type, and so on. And then Truffle feeds that, runs through that code a few times, figures out how the actual application flows, and then dumps that to Graal, and it knows how to do all the Graal stuff for you. So all you do is write an interpreter, it traces through it and figures out how to optimize it, and you get it JIT for free. Has anybody ever played with PyPy or looked into PyPy? Again, same sort of concept there. The idea that you write an interpreter, but the act of writing that interpreter gives it enough information to write a JIT too. That's what we get with Truffle, and this is actually working today. So Truffle, all we need is over here on the left. JVM language goes down to some AST. We've got some Truffle superclasses. We've got some Truffle annotations to say how the application flows, where the data flows through that language, what the semantics are. And then it does all the rest of this for us. Turns it into Graal intermediate, Graal optimizes that, turns it into native code, and it's really impressive how well it works. So impressive that they're actually doing Ruby implementation for us right now in JRuby. This is Chris Seaton. He was brought in as an intern a year and a half ago or so into Oracle Labs, essentially just to work on a prototype of a Ruby implementation on top of Truffle, to see what we could do, see if we could solve the hard challenges of implementing Ruby on top of this framework. And here are some of the early results that he has. I want to say this is research level. Oracle Labs should be an indication that this is research. If I was at Oracle, I'd have a big disclaimer slide in front of it too. But I'm not, and of course this is the future, so it's awesome. Buy this stuff, it's great. But these are the numbers. The bottom's a little hard to see. On the far left here, we have JRuby 1.7 something running on Invoke Dynamic. So generally our best performance that we can get generally the best performance that the Ruby community can get right now as far as running applications. The middle one, not as interesting. This is Ruby on top of Truffle without Graal being in play. So it's just the interpreter, just doing all of its JVM level optimizations. And they can get close to what we can do with Indy in some cases, but they're mostly slower. The interesting one, though, is when Truffle and Ruby run on top of Graal, we get 5, 10, 20%, or 20 times improvement on performance, especially on things like numerics, where Truffle is very good at saying, okay, I don't actually need a fully boxed number object here. Let's just pass the long through. Let's pass the int through. The kind of stuff that's forced languages like Groovy and Clojure to add primitive types, integer and long and whatnot, into their function declarations, we don't have to do because Truffle can see through that. Yeah?
I'm not clear. What do the numbers mean on this
The
chart?
numbers here are the number of times faster. JRuby with invoke dynamic is baseline 1. And so we're talking 20 times faster on the Mandelbrot benchmark, which is all 64-bit decimal. We have to turn those into objects. There's a crap load of them being spun at runtime, and the JVM just doesn't see through that well enough. Truffle actually can. Truffle will see that all you're ever doing is plain old 64-bit double operations here. Let's not allocate the object. Let's just use the raw bits, and they're able to get this kind of performance improvement out of it. Very cool stuff. So I mentioned that Ruby Truffle is now part of JRuby. We saw this presented in 2013 at the JVM Language Summit, and we were really excited about this. Unfortunately, they were doing it as closed source, and it was all research, and they were like, I don't know, we'll see what we can do with it. But we lobbied Oracle, we worked with them, wrote a bunch of emails, complained a lot, and they actually gave it to us. They rolled it into JRuby proper under our licenses. Chris is continuing to work on it. They're funding at least 2 other full-time developers to work on Ruby Truffle as part of JRuby. I mentioned there's other languages. They have a JavaScript implementation that is it's not open source currently. May or may not be in the future. You never know what Oracle's going to do. But it is as fast or faster than V8 as far as running JavaScript once it gets warmed up. They've kind of brushed startup time under the carpet at this point. But it is impressively fast once it actually warms up and runs. They're also starting to use this for JVM Java features. Project Sumatra is the work on doing GPU utilization at the JVM level. So if you do a massively parallelized operation over an array of numbers, it'll automatically turn it into GPU calls and do it all in parallel. The early work has actually been built on top of Graal. So this is something that probably will get into a future JVM release at some point. These numbers are also forcing the hotspot folks to deal with some of these optimization issues that they haven't in the past. Things like eliminating objects, escape analysis, eliminating all these integer boxes. Even in regular Java, eliminating var args, array boxing, when you don't need it. If you're only passing one argument in, why do you create an array for it? Well, the JVM forces you to. That's the kind of stuff that the hotspot folks are going to start fixing because Truffle and Graal are able to do such a good job of it. All right. So that's most of what I have. I want to just summarize here. Hopefully what we've learned or what you're thinking about with all these projects that are out there. There are problems on the JVM, like different languages, new features, getting code to optimize down to something the processor wants. There are problems, but we can fix them. We've got tools like JNR, we've got tools like Invoke Dynamic and Graal and Truffle that are coming along. These are all open source projects, with the exception of the JavaScript implementation that Oracle has. This is all open source. And the Truffle and Graal stuff is just part of OpenJDK. So it's under the same GPL terms as everything else in OpenJDK. And you can go look at it. You can look at the Ruby Truffle implementation in JRuby. They have some toy languages. This is stuff you can use today and play around with right now. And I don't think anything is really impossible. We can get tail calls. Still people talking about that, playing with tail calls on the JVM, getting coroutines, proper coroutines built into the JVM. There's prototypes of that stuff. You can get involved and make all these things happen. If there's something that you wish you had on the JVM, well, we can do it because it's all open source and it's all available there. So that's all I have today. Thanks very much. I hope we have some time for questions and hanging out afterwards. All right. So yeah, in the back.
question, not even a technical one. So what's it like working with the JVM or on the JVM and being outside of Oracle? Can you talk about that process a little bit?
So what's it like working on the JVM, trying to push the JVM forward and being on the outside? Honestly, all the JVM folks that I deal with at Oracle, with very few exceptions, are the same guys that were at Sun that were totally on board with open source, just trying to get people involved. They're absolutely thrilled when someone comes in and says, hey, I want to try and help out. Even if it's just, I've got this weird case and it doesn't seem to optimize well, they jump on that stuff. They love to see that. Getting changes into the platform is not so much an Oracle blocker as it is just a very cumbersome process. But Oracle's been doing an incredible job of making that process easier, the new version of JCP, and then also the JEP stuff. If there's something at the VM level that doesn't have to go through an approval process, it's much easier to get something into OpenJDK than just get it in as a JSR. So it's been pretty good working with them. It's mostly trying to get through the inertia of the past. It's becoming more and more of an open platform as Oracle evolves it. I've been pretty impressed. Other questions? Yeah, over here.
What JRuby ops would you use depending on the environment due to how they affect things like invoke dynamic in test or development or production? There used to be nail gun. I never got that working, but there's like dash server, things like that.
Right. So for JRuby, we have one of our big challenges has been that you can pass as many options as you really want to the JVM and tune it in a whole bunch of different ways. We've tried to find the happy medium of options. So normally JRuby will not run with invoke dynamic support, mostly because although it gets us the best straight line performance, memory consumption is fairly high. It's maybe 50% higher than normal because of all the extra code generation, and startup time is considerably worse. Startup and warm-up time are a lot longer. So normally JRuby will run without those things on. Startup time-wise, we even turn off our compiler and several JVM features with the --dev flag that usually will give you about 50% improvement on startup on pretty much any platform. And then there's other ways you can tweak it from there. I have extra slides here for that, for anybody who wants to see them. For tuning for production, if memory-wise and warm-up-wise things look good in a test or QA environment with Invoke Dynamic, we recommend that most of the time. It will get the best performance eventually. It's just the JVM takes a little bit longer to get there, startup and warm-up and so on. Other flags, I mean, it just comes down to standard JVM tuning at that point, with the thought in mind that Ruby is extremely object-heavy. Strings and arrays and hashes being created and thrown away like mad. So tuning the garbage collector for that, and then hopefully the JVM guys will get better escape analysis and whatnot. So, but yeah, I mean, it's all that tuning is an ongoing discussion. It really kind of depends on the application, but we're willing to talk with you more about it. Yeah.
Things like Project Raw and truffle effect debugging. So like when something goes wrong, if you're in IntelliJ or Eclipse, are you getting help from the tools, or is it just seg fault, buddy? Good luck.
Right. Well, so the question's about how does truffle and grawl and those lower level items affect debugging? Well, for the native calls, you're on your own. I mean, unless you're doing all of your Java debugging in GDB or something, you're probably going to be stuck at that point as far as making a native call. You're calling out of the safe zone. But truffle and growl, I'm sure you could get growl to emit bad code that would crash the JVM or something. But in general, it still has to obey all of the semantics of the JVM, memory protections and whatnot. Debugging-wise, the truffle folks have started to look into that more seriously. They actually have very extensive debugging capabilities that can be on all the time, because they can just de-optimize anytime they want and say, okay, well now you're stepping into this frame. I'll show you all the frames that have called it. I'll show you all the possible callers, all the types I've seen here. They have a lot more of that information available at runtime because it's all running above the JVM level. So they have that information. That said, it is still a research project. It will crash. It will have missing features that if they were just JVM based, you would get for free. They're not there in Truffle and Growl right now, but they are focusing on largely language performance. What's the best case for building a language on top of this, and then building some of those features after the fact? Other questions? Yeah.
For users of JRuby, do you have for the various versions 1.7 and the upcoming 9,000? Do you have a general recommendation about versions of Java to pair with your JRuby? Java 7 versus Java 8, Java 9?
We always just recommend whatever the latest is. I mean, there have been some rocky times where, like, early Java 7 releases on OS 10 were a little flaky and so on. Early releases that came out on BSD weren't so great. But in general, like, going from Java 7 to Java 8, it's like, even now, it's like free 10 to 20% performance, just magically out of somewhere. And those changes eventually trickle back down to the older JVM versions, but yeah, we recommend people to use the newest stuff. There's also the issues of security. Security fixes come out first for the newest JVM versions. And as we know now, the JVM is not a perfectly secure platform, so it's probably a good idea to stay on the latest one anyway. And there's really no reason not to. We've only run into a handful of minor things that have broken as forward releases.
Do you have any comments on the Scala and Scala APIs?
Comment on Scala and what?
Scala APIs like STM, futures, lambda.
Well, I love all the languages and what they're doing with the JVM. I would like, you mentioned STM specifically, I'd love to see if there's anything the JVM can help with there to make it faster. There's possibilities of being able to use invoke dynamic for things like that, especially for if you've got a ref that's always the same except for that one time. Well, we would just totally avoid the traversal of that ref in between. Invoke dynamic can optimize that away and make it a VM level bailout when you actually have a transaction that needs to cancel or something. Yeah.
So on that, 292 had at one point a call out for save point and the whole semantics around that being exposed, which would have made this whole thing a lot faster, right? Because we had a direct point to swap when necessary. Do you know what happened there? Like why it got taken out?
It's still there, but it really only optimizes well if you emit it into bytecode. You can call it's the switch point API in method in Java lang invoke, and it is still there. Switch point is essentially an if then else that you can only turn off. It follows the then path for as long as it will, and you can turn it off once. That corresponds to something in the JVM called a safe point, where it says, okay, if you reach this point in the code and an assertion has failed, bail out completely, throw that code away and never come back to it again. That's where it branches back into the interpreter and starts re-optimizing. But that's a Java level concept in invoke dynamic, that you can have a safe point as a normal object. It is still there, but in order for invoke dynamic to optimize switch points and handles and whatnot, you kind of need an invoke dynamic entry point, the bytecode for it. So the compiler could emit, okay, an invoke dynamic that's going to go into a ref that probably hasn't changed. Here's the switch point that checks whether it's changed. And then until it actually does change and there's something different at that ref, it would be almost a no-op to traverse it, rather than what we have now with refs, which is much heavier. So yeah, there's a lot of those features we could do better on.
Is there a particular language that you feel would not be a good fit to run on the JVM as far as syntax or functionality?
Basic.
Basic would be awesome on the JVM.
Well, usually the problems of bringing a language to the JVM are either native access, which was one of the things that we worked hard to solve in Ruby, or just call flow, call protocols and whatnot. Most of the Lispy-like functional languages really wanting tail calls to work. Languages like Ruby or Python having a generator or coroutine concept that we just don't have on the JVM, lightweight threadlets, green threads essentially. Those are the things that are a little bit of a challenge. Those are slowly starting to come along, but for example, Go is one that would be very difficult to implement on the JVM right now. You need VM level understanding not only of all the I/O channels you're dealing with, but of the flow of code and how to interplex those together and maybe have 5 threads that run 5,000 coroutines at the same time. That's the kind of stuff that's currently still difficult on the JVM, and it's next areas to push.
someone else has.
No, go ahead.
To piggyback off of that, like, are there any plans for interop with the Go language as kind of like a native binding similar to what you were describing?
No plans that I know of. I don't even know what Go emits as far as like a shared library sort of thing. If it emits something that looks like a C entry point, we can use our native stuff to call into it. But otherwise, I don't know of any plans specifically to integrate with Go at this point. Yeah.
I recall you saying once that the JRuby actually has a Ruby VM that you wrote that the Ruby runs on top of. So you're actually implementing a VM to run on top of a VM.
Yeah.
I was wondering if you had anything that you wanted to share about that, if that's something that other JVM authors need to do or consider.
Well, there's a reason why I've been forced to learn about how the JVM works. It's because we've essentially implemented a little mini VM on top of the JVM. JRuby is one of the only JVM languages that has an interpreter and a compiler. JRuby code, Ruby code that runs on JRuby will run in our standard interpreter for a little while, and then as it gets hot, like the JVM does, we will turn it into JVM bytecode. And then the JVM bytecode will run that for a while and then turn that into native code. But it's enabled us to be able to have much faster startup than languages that are all compiled. They don't have to load all of that bytecode at the same time. And it allows us to do our own optimizations at runtime. We can actually do some of the same profiled optimizations the JVM does above the JVM. The Nashorn guys are considering this because they're purely bytecode generation, and it's a major hit for them to try and boot all that bytecode up at runtime. There are challenges like getting a proper backtrace out of that. When we have just interpreter frames on the JVM stack, we have to restructure it. But it's been an interesting thought experiment, and I think it's paid off in the long run as far as JRuby goes. We're the only JVM language that has anything like that.
We got like 2 more questions.
2 more questions, all right. Far back.
How do you feel about the future of Ruby's, I guess, mainline C implementation, given all this work that's been going into JRuby and the alternate implementations like Rubinius?
So I would say, as far as the other Ruby implementations, they all definitely still have their areas where they're better choices than JRuby. MRI, the standard C implementation, is still, it's blindingly fast to start up. Like what takes us 2 seconds to do, it takes them, 1/100th of a second to do. They just start up immediately. So anything that you're doing that's like a low-level Unixy scripting sort of thing, system-level scripting, for sure you want to use CRuby. It's just a better choice for that. Rubinius, if you want essentially like the full set of POSIX capabilities, and you have a lot of C libraries, native libraries from the Ruby world that you need to use, and you can't get away from that, well, it gives you some of the VM features of the JVM without abandoning your entire code base. Most applications will drop in without a lot of modification. You don't get all the benefits of being on the JVM, but you get a lot of the benefits of a managed VM with a real GC and so on. I think all these implementations still have strong use cases. They're very important for the community. And CRuby in particular, it's not a particularly complicated implementation. It's easier for people to contribute to that implementation or to contribute to Rubinius because it's largely Ruby for the core stuff. They'll continue to live on for a long time. As a viable deployment platform for a server application, I think it's going to be more and more difficult to justify CRuby if they don't get things like real parallel threads, if they don't get things like a full-on generational garbage collector. But for certain types of applications, both Rubinius and MRI are still the best choices. And then right in front of them.
Yeah, we've tried to use JRuby for sort of highly concurrent web applications and run into issues where even when the underlying database and CPU are running pretty cool, we see transaction times escalate pretty high as concurrency increases.
Okay. And
it seems to be related to lock contention. Have you heard that from anywhere else or looked into that at all?
Sounds like a bug report to me. We've had various folks that essentially they just look at where it's spending a lot of time. On a if it's low CPU and it seems to be blocking forever, it's pretty easy to get a thread dump and see what it's sitting on, what lock it's waiting on, what locks are in play. There's lots of tools to find that stuff. And for one user, after just a few rounds of him submitting bugs and us patching stuff, we increased his throughput like 10 times or something, because there were just dumb things that we had, legacy code that was within JRuby. You should, unless you're totally saturating the memory pipeline, like you've got so much allocation that you can't even push any more data through the memory pipeline, you should be able to saturate all the cores with a JRuby application. And if you're not, it's either something wrong contention-wise on your side or something that we can improve. So,
what's the information that you'd like to have when a bug like that's submitted?
Stack dumps, even like sampled profiles, doesn't have to be fully instrumented profiles. Sampled profiles that show we've got a lock acquired here, and these other threads are all sitting waiting on that lock. It's not too hard to find it. And there's additional tools. There's visual VM tools for tracking lock contention and stuff. Anything that you'd use to figure that out and at the JVM level should work fine for JRuby too. JStack? JStack, yeah. That'd be the basic thing. Give us a stack that shows some contention. And that's it. Thanks very much.
All right, now here comes for the part of you. We get to give away one free ticket, right?
Yeah.
So we need a random number generator. So that's Charles.
And it's 1 through 47.
47. Oh, okay.
Have a beer.
So yes. Well, let's just go with 42 because that seems like the right.
Oh, that's awesome.
Great. 42 is Jerry Cattell.
See here? All right.
Yeah. I didn't want to look around too much because someone was going to subliminally like.
That's awesome.
I will. Yeah.
Excellent. All right.
We'll see you there.
Oh, yeah.